So how does this work? Now, it'd be nice if it was like the sum rule. We just take the derivative of f, take the derivative of g, multiply them together, and we're done with it. But it don't work that way. So the kind of intuitive version, I'm not going to prove this right now. The intuitive version is related to the derivative of a constant multiple. So if we take the derivative of some constant, like 2 times the sine of x, for example, then that constant can just be ignored for a moment, and we can multiply it in after we take the derivative. So it's just whatever the constant is times whatever we think f prime should be. And that's kind of what happens up here, but the problem is neither f of x nor g of x is a constant, but what we do is we just kind of make believe. So I think about g of x for a minute here. Actually, yeah, let's just make believe g of x were just a constant. If it were just a constant, then this derivative here, which is a different color, would be just f prime of x times that constant, which I'm calling g of x instead of c. Okay, problem, g of x isn't a constant. So this could go the other way. It could be f of x that's the constant, meaning it just hangs out, and I multiply that by g prime of x. And it turns out if we combine both of those ideas, that is the product rule right there. So you take the derivative of one function, multiply, leave the other function alone. And you take the derivative of the second function, multiply by the first function, left alone, right? Which is kind of related to that constant rule. We get a sum in the middle here. So products are not straightforward. However, this is the pattern. The book has a proof of why this is the case. I just did my intuitive version of it, why I think it ought to be true, but by no means what I just said is a proof. But let's test it with an example. Okay, so the test is going to be on a function that we could do with or without the product rule. So I'm going to say my function is, I'm going to write my derivative notation here that I want to take the derivative of the function x times 2x plus 1. Now, I don't have to use the product rule here because I could distribute that x through there. So just note, I could write it this way. And sometimes it is worth doing algebra before you take a derivative. It can make your life way easier. This is also the function 2x squared plus x. And based on our work with polynomials and the sum and power rules yesterday, we know that is going to be derivative of x squared is 2x times 2 is going to give me a 4x. And then the derivative of 1x is just 1. Right? So in this form, I learned yesterday how to take the derivative. I'm going to apply the power rule to this. So this one right here is my f of x, and this one right here is my g of x. And so the product rule says take the derivative of f of x. Well, the derivative of x is 1. And then just multiply by the other function as is, 2x plus 1. And then leave the first function alone. So I don't mess with the x, I just leave it. And then multiply by the derivative of the second function. Well, 2x plus 1, its derivative is just 2. Another way to think about that is what's the slope of the line 2x plus 1? Well, it's 2. So the slope is the derivative. And if I clean that up, I get 2x plus 1 plus 2x, which is 4x plus 1. All right, so this is just a simple example showing that this formula seems to work for this particular function. And I know it works because I can check by doing the derivative a different way with a little algebraic trickery, just rewriting the function. Okay, so there's two morals here. One, this is the formula if you have a product of two functions, that's what the derivative is. Derivative of the first function times the second plus the first function times the derivative of the second. It's complicated. Here's an example of it working right there. The other moral of this thing right here is, I forgot. Oh, I remember that sometimes it's better to do something algebraically to the function and then take the derivative, because you might find an easier way to do it. This is the hard way. In this case, that's the easy way. But sometimes we have no choice. We have to do that way. So let's do some more examples.